In this video, we're going to we're going to discuss how we can use another method, the addition method, to help us solve systems of equations. All right, so we're going to be looking at the addition method. All right, with the addition method, these are some steps that I take and I use to help me solve using the addition method. Again, since we have two variables, we got to come up with a way to eliminate one of the variables. And so sometimes this method is also called the elimination method. But what we're going to do is we're going to multiply to get opposite coefficients on one of the variables. Opposite coefficients. And what I mean by opposite coefficients, for instance, if I see a 2x and I want to get a opposite coefficient, then the opposite of 2 would be negative 2. Or if I have something like, 7x, well, the opposite would be negative 7x. All right? We're going to multiply to get opposite coefficients on one of the variables if we don't already see those opposite coefficients. So sometimes the problem we'll have with opposite coefficients already, but if we don't see opposite coefficients, we're going to multiply, do some kind of tricks to help us do that. Next thing we're going to do is we're going to add the equations together, right? Since both sides are equal in both equations, if we add them both sides together, then they're just going to be equal as well. So it stays a true equation, all right? This step is the addition step when we actually add the two equations together. Then we're going to solve for a variable because one of the variables will be eliminated and we'll have an equation with one variable. So we'll solve for that variable. Then we're going to back substitute into one of the original equations to help us find the value of the other variable. Let's look at an example. First example, 2x minus 9y equals 33. 4x plus 3y equals 3. I want to solve this using the addition method, all right? And so what I'm going to do first is I'm going to try to get opposite coefficients in front of my variables, or in front of one of my variables, all right? Let's say that I, out of the blue, pick, let's say, y. Let's look at these y's here. I got a negative 9y and a 3y. If I want opposite coefficients, all right, I got to kind of think about the least common multiple of 9 and 3. Like 9 was in the denominator and 3 was in the denominator. Then the least common denominator would be 9, right? Since this is a negative 9, then I want to multiply this 3y so that I can get a positive 9. That means I'm going to multiply both sides of this equation by a positive 3, okay? When I do that, my system is going to become this system right here. I'll have a 2x minus 9y. That first equation is going to stay the same. But my second equation, I'm multiplying both sides by 3, and you can write it like that. Multiply both sides by 3, like we normally would. And I'm going to end up with a 12x plus 9y equals 9. And as you can see, I do have those opposite coefficients. I have a negative 9 and a positive 9. Now that I have that, I want to add my two equations together. 2x plus 12x is 14x. 33 plus 9 is 42. Notice those cancel, so I don't have those anymore when I add these two equations together. I can divide both sides by 14. And when I divide both sides by 14, I'll get x equals 3. All right, so my x coordinate of my solution, which of my ordered pair, is 3. Now I can just go back and substitute 3 into one of my original equations, right? So I'm going to back substitute here. All right, I'm going to abbreviate that. Let's say I substitute into my first equation. 2, instead of writing x, I'm going to write 3 minus 9y equals 33. Well, that's 6 minus 9y equals 33. If I subtract 6 from both sides, I subtract 6, get negative 9y equals a positive 27. I can divide both sides by negative 9, and I'll get y equals negative 3. So my solution, 3, negative 3, and this will be independent. Independent system. Okay, let's look at some other examples. In this example, I have 4x minus 3y equals 21, and the equation 8x minus 6y equals 42. Again, We get to choose which variable we want to have the opposite coefficients for and which equation we need to do the multiplication. Sometimes we want to multiply one equation. Sometimes you're going to have to multiply both equations. But let's say I want opposite coefficients on, let's say, the x this time. All right. Well, I have an 8 and a 4 as my coefficients, right? One of them needs to be negative, one of them needs to be positive, and they have to be the same coefficient, the same actual number in absolute value. Well, I think 8 is my lowest common multiple between 4 and 8, right? 4, 8, 12, 8, 16, right? 8 is the lowest common multiple. So since this is a positive 8 here, I want this to be a negative 8, so I'm going to multiply both sides of this equation by negative 2. When I do that, I'm going to get this equation here. Negative 8x plus 6y, right? Remember, you have to use your distributive property here, right? Equals a negative 42. And my other equation is going to stay the same. 8x minus 6y equals 42. Now that I have my opposite coefficients, I got my negative 8 and my positive 8, I'm at a great point where I can add my equations together. Well, negative 8x plus 8x, that's canceled. That's 0. 6y, minus 6y, that's also 0. So my left-hand side became 0. My right-hand side, I have a negative 42 plus 42. That's also 0. Well, since that's also 0, this is what we call an identity equation. And when we have an identity, that means we have infinitely many solutions. And so with infinitely many solutions, instead of saying all real numbers, since I'm talking about a system of equations, I know that I have a dependent system. With dependent systems, I write my ordered pair x, comma, instead of writing y, I have to solve one of these equations for y, and I'm going to put what I have y equals into this spot here as my y coordinate in my ordered pair. And so I'm going to take this, let's say I take this first equation, 4x minus 3y equals 21. I'm going to solve this equation for y, and that'll give me the other part of my ordered pair, right? So if I subtract 4x, I get negative 3y equals negative 4x plus 21. And then I can divide both sides by a negative 3. So I have y equals, well, negative 4 divided by negative 3 is a positive 4/3 x. And 21 divided by negative 3 is minus 7. And so my ordered pair, or my solution in terms of all x, would be 4/3 x minus 7. Okay? And again, if I were to ask you what would the graph look like, well, the graph would look like one line, right? They would be lines that lie on top of each other. So those equations up there are actually multiples of each other, all right? If I multiply this one by a constant, I get to this equation right here, basically. All right, let's look at another example. 3x equals 4y plus 11. 9x minus 12y equals 30. Now, if you look at this system here, it looks a little weird because it's not set up exactly like we want it. We want our stuff to actually line up so we can see our opposite coefficients and so that we can combine like terms pretty easily. So what I'm going to do here, instead of having this 4y on this side, I'm going to subtract 4y from both sides, and this equation is going to end up being 3x minus 4y equals 11. All right, and my second equation is going to stay the same. It's a lot easier to solve these problems when everything is lined up perfectly. Now that everything is lined up, let's go ahead and try to eliminate one of these variables by getting these opposite coefficients and then adding. All right. Let's say I wanted to get rid of this let's say the y this time. Well, I have a negative 4 as a coefficient and a negative 12 as a coefficient. Right? I know that one of them is going to be positive, one of them is going to be negative. And between 4 and 12, the least common multiple between 4 and 12 is 12. And so I want to make this negative 4 a positive 12. So I'm going to multiply this top equation on both sides by a negative 3. Okay. I've got to use my distributive property on my left-hand side. So this system is going to become this system down here. I'm going to have a negative 9x plus 12y equals negative 33. And on my second equation is going to stay the same. Now that I have opposite coefficients on my variable that I've chosen, the y, I'm going to add my two equations together. Well, negative 9x plus 9x, whoa, those are actually opposite, so that's 0. 12y minus 12y, that's also 0. And on my right-hand side, negative 33 plus 30 is a negative 3. Well, 0 definitely doesn't equal negative 3. Remember, we call these contradictions. And so since I have got a contradiction here, I know that I have no solution. All right? And if I ask you what type of system we have here, I would say inconsistent. All right. Okay. And so if I were to ask you what would the graph of these two lines look like, you would say that they'd be parallel, because anytime we have parallel lines, they don't intersect, meaning we don't have an ordered pair. That would be a solution. All right, we're going to look at one more example. And this one's a little bit more complicated. All right. What we're going to do here is we got some fractions. We're going to look at these fractions. We got 2/3 x plus 5/4 y equals 12. X minus 7/2 y equals negative 25. What's hard about fractions is getting those coefficients opposite. Okay? Just as we would do if we had just linear equations and we were just solving in one variable, we would clear our fractions. That's what we're going to do first. So before we even think about getting our opposite coefficients, what I'm going to do is I'm going to clear my fractions. All right? I got a 3 in the denominator and a 4 in the denominator. Their lowest common multiple, at least common denominator, would be 12. So I'm going to multiply both sides of this equation up here by 12. In my denominator here, my lowest common denominator is 2. So I've got to multiply both sides of this equation by 2. All right. Of course, we're going to use our distributive property. And our system is going to come over here. All right. 12 times 2/3. Now, 3 goes into 12 4 times, and if I multiply 4 by 2, I get 8. So that would be an 8x. When I distribute the 12 to the 5/4, 4 goes into 12 3 times, and if I multiply 3 times 5, I get 15. So that's 15y, and 12 times 12 is 144. When I distribute here, in the second equation, I'm going to get a 2x. And when I distribute to that 7/2, 2 goes into 2. The 2's cancel, and I'm left with just a negative 7y equals negative 50. Okay. And so what I want to do now is get opposite coefficients. All right. I'm going to choose one of my variables. Let's say I choose x. All right. If I choose x, the lowest common multiple between 8 and 2 is 8. All right. Since this is a positive 8, I want this 2x to become a negative 8x. So I'm going to multiply both sides by a negative 4. So this system, my first equation is going to stay the same. But my second equation is now going to become a negative 8x plus 28y equals 200. Now that I have my opposite coefficients on my x, right, 8 and negative 8, I'm going to add these two equations together. The 8x's cancel. I am left with a 43y equals 344. Of course, we can divide both sides by 43. And we'll see that y equals 8. Okay. So now that I know the y coordinate of my ordered pair, that's my solution, I'm going to substitute it into one of the original equations. Let's say I go back to x minus 7/2 y equals negative 25. This is where I'm going to back substitute. And so y is now 8. So I get x minus 7/2 times 8 equals negative 25. Well, 2 goes into 8 4 times. So that's x minus 28 equals negative 25. I can add 28 to both sides, and I'll have that x equals 3. And so my solution would be 3, 8. One of the things that I didn't discuss before is being able to check your solution. All right, you can always check your solution by substituting your ordered pair back into your original two equations and making sure that you get a true statement. So there should never be any doubt at the end, or if you do doubt, you can always check your solution by substituting in your equation, into both your equations in your system. All right, our last example that we're going to look at involves an application problem. It says a man bought roses and carnations for his wife on Valentine's Day. Each rose cost $6 and each carnation cost $4. If the man spent $68 for a total of 15 roses and carnations, how many of each type of flower did he buy? Okay. Again, we're talking about systems of equations here in two variables. So we know that, our variables, I'm going to have two of them, are going to be basically what they're asking us for. And they're basically asking us how many roses and how many carnations. So I'm going to let X represent the number of roses. I'm going to let Y be the number of carnations. All right, now that I know X and Y, what they represent, now it's time for me to write my equations. All right, and this is very similar to a problem that we've done before. Each rose costs $6. Each carnation costs $4. The man spent a total of $68. All right. Total of $68. Well, the money is going to be coming from the amount of roses times the number of roses plus the amount of carnations times the how much the carnations cost. Right. So I'm going to have 6x. All right. That's the amount or contribution from the roses in the cost, plus 4y, that's the amount of money that's contributed to that $68 from the carnations. And if I add those two amounts of money, it should give me the total of $68. Okay. It says if the man spent $68 in total, $68 for a total of 15 roses, well, this total of 15 roses tells me, roses and carnation tells me how many flowers or roses and carnations I have. And so since X represents the number of roses and Y represents the number of carnations, if I add those up, they have to equal 15. All right, so those are my two equations, and now I'm going to solve this using the addition method. All right, I got to get opposite coefficients. And so let's say we get opposite coefficients on the Y. That means since this is a 4, there's a 1 in front of that Y. I'm going to multiply both sides of this equation by -4. All right, by multiplying both sides of that equation by -4, I get this new system, or the system that looks like this. It's not new, it's the same system. But it'll have a -4x minus 4y equals -60. Let's add these two equations now that I have these opposite coefficients here and here. Well, I get a 2x, those cancel, equals a +8. If I divide both sides by 2, I'll have that x equals 4. So I know that he has 4 roses. All right, now I'm going to back substitute to determine the number of carnations. All right, well, if I can either go to this equation or this equation or this equation. I'm going to go to the equation x plus y equals 15. And since I know that x is 4 from before, I have 4 plus y equals 15. Sorry about this mess here. And I can subtract 4 from both sides. And we'll have that y equals 11. So we have 4 roses and 11 carnations. That would be my solution. And this concludes our study of solving systems of equations by using the addition method.